This is lesson 3 in our unit on electrochemistry. And a big change takes place. In the first 2 lessons, everything was about spontaneous electrochemical cells called voltaic cells, or what everybody calls a battery. In a voltaic cell, electrical energy is produced from chemical energy. Or, another way to say it, is we are turning chemical energy into electrical energy. The rest of this chapter is about electrolytic cells, which are just the opposite. In an electrolytic cell, we are turning electrical energy, which has to be provided, into chemical energy. That chemical energy might be the process of electrolysis, and it might be the process of electroplating. Both electrolysis and electroplating require electrical energy to do chemical work. Remember, both energy and work are measured in joules. Now, there are 3 kinds of electrolysis. You can pass electrolysis through water, 100% H2O, 0% salt. You can pass electricity through pure salt, 100% salt, 0% water. Of course, this won't work unless the salt is liquid, because when you have liquid salt, then the ions that make up the salt can be mobile. To conduct electricity, you have to have mobile charged particles. Thirdly, you can have the electrolysis of a saltwater solution, often called brine. The electrolysis of a saltwater solution is covered in a separate screencast, lesson 4, in your folder. Now, when we talk about the electrolysis of water, we're talking about passing electricity through water, which causes it to decompose into hydrogen gas and oxygen gas. In other words, as electricity goes through water, it separates the hydrogen ions from the oxygen ions. Now, the hydrogen ions, because they're positive, will be attracted to the negative electrode. And of course, that negative electrode is negative because it's hooked up to the negative post of a battery. And because it's negative, the hydrogen ions are going to be gaining the electrons, or the negative charge, that's been pushed there by the battery. So this is going to be reduction, the gaining of electrons. In the electrolysis of water, the decomposition of water, the hydrogen is going from a +1 ion in water to 0 as hydrogen atoms, and the hydrogen atoms, of course, pair up and become Brinkelhoff hydrogen gas, which bubbles at that electrode, the cathode electrode. Meanwhile, the oxygen ions, with their full outer shell of 8 electrons, will lose 2 of their electrons, becoming oxygen atoms. And they'll lose those 2 electrons to the positive electrode, opposites attract, and the positive electrode will transfer the electrons back to the positive post of the battery. Meanwhile, the oxygen ions, which have lost their electrons to become oxygen atoms, they pair up and bubble off as oxygen gas, Brinkelhoff diatomic oxygen gas. And of course, that is going to be going on at the positive electrode, the anode, and the loss of electrons from the oxygen ions to turn them into oxygen atoms, that's oxidation. Loss of electrons is oxidation. Now, what about the electrolysis of 100% salt? Of course, it's got to be very hot in order to turn into a liquid. And when we do that type of electrolysis, once again, you're going to take your salt and you're going to break it down into its if you were putting salt into water, the salt would dissolve and the salt would break down into its positive and negative ions. Now, if we wanted to go the other direction, then the sodium ions and the chloride ions would come together to make salt. So, think about the reaction of pure sodium chloride. And this time, since there's no water, it's not going to dissolve to form sodium ions and chloride ions. It's going to be pulled apart by the electricity into pure sodium and to pure chlorine. Chlorine, of course, Brinkerhoff, diatomic, means our balanced equation is 2 sodium chlorides becomes 2 sodium atoms and 1 molecule of chlorine gas. So the sodium is going from +1 to 0, just like the hydrogen went from a +1 to a 0. This would happen at the anode, and this would happen at the cathode, where reduction takes place because the sodium ions would be gaining electrons delivered to the electrode, the inert electrode, from the negative post of the battery. Meanwhile, the chlorine ions, the chloride ions, they would be attracted to the positive electrode, negative attracted to positive. The chloride ions would lose its electron, becoming chlorine atoms, and the chlorine atoms would pair up and become chlorine gas. And you would have chlorine gas bubbling at the positive electrode, the anode, where oxidation takes place. And of course, that would be a very dangerous reaction. If you could get a temperature hot enough to melt salt, several thousand degrees, you could get pure sodium and pure chlorine, both of which are dangerous because pure sodium, as you recall, blows up in water. Pure chlorine is a deadly gas. Now, before we move on, we should mention something about electroplating. In electroplating, we take the object that we want to plate, to cover with metal. In this picture, a key, but it could be a piece of jewelry, it could be a coin. And you want to hook it up to the negative post of the battery. That makes the key the negative electrode. And because it's negative, it's going to attract the positive metal ions that make up the electrolyte solution. As a result, your positive ions, in this case copper, are attracted to the negative electrode, the key, where it gains electrons, becoming copper atoms, and the copper atoms cover the key. And of course, the gaining of electrons is oxidation, is reduction, and reduction always takes place at the cathode. Meanwhile, on the other side, those copper ions that are in solution, this could be copper sulfate, copper chloride, copper nitrate. These copper ions in solution will be depleted as they coat the key, unless your other electrode, the anode, is made out of the same metal, copper. This is hooked up to the positive post of the battery, so as the copper atoms that make up the anode are losing their electrons going back to the positive post of the battery. The loss of electrons is oxidation. That takes place at the anode. And as the electrons leave, the copper atoms turn into copper ions, which go into solution. And so as long as your anode is present and hasn't run out, hasn't been totally used up, you can continue to coat the key or the coin or the jewelry or the spoon or whatever it is with copper. If I wanted to coat it in silver, I would need silver nitrate solution and a silver electrode. That's what electroplating is. And here's a bit of the example of heating up salt so hot till it turns liquid, and then separating the ingredients of the salt, the sodium from the chlorine, producing sodium metal and chlorine gas, like we talked about previously. Your net ionic equation at the bottom of the page shows your sodium ions from sodium chloride gaining electrons, reduction, and your chloride ions losing electrons, becoming chlorine atoms and pairing up. That's oxidation. And so you have sodium forming at the cathode, the negative electrode, and chlorine gas forming at the anode, the positive electrode. You add these two half reactions together, and you can see your molten sodium, sodium ions and chloride ions, not aqueous, but in a liquid, as a liquid, molten liquid, turning into pure sodium and chlorine. On your test, you might have to show the electrolysis of water, the electrolysis of a molten salt, the electrolysis of brine, or electroplating. Now here's your textbook's discussion of the electrolysis of an aqueous solution or brine. And they use sodium iodide, but in the lesson 4 screencast, I used potassium iodide, which is a demo I would have done in class if we were there. So I'll leave these 3 pages, since we've already talked about it, and come to the very last part of the chapter, which includes a little biographical sketch of Michael Faraday, my favorite physicist, the most famous experimental physicist of the 19th century. If they gave out Nobel Prizes back then, he would have gotten 6 of them. Began work as a boy, was a devout Christian man, probably of a Quaker kind of faith, very separatist. He worked for another famous chemist, Sir Humphrey Davy, when he got kicked out of school as a boy because he had trouble pronouncing the letter R, so kids laughed at him. But that's all part of God's providence. And then one of the first books he saw that fascinated him was a book on chemistry when he worked for a bookbinder, which got him interested in science, and got to work for Sir Humphrey Davy, who would put on science shows. And in the end, he too became an educator and was a wonderful speaker, according to biographies, and gave many lectures to the general public, helping them to understand this new science. He also discovered other things in chemistry, as well as such as benzene, and he had an awful lot to say about generators and motors and transformers, because he did a lot of work in electromagnetic induction, something you'll learn a lot more about in AP Physics. All right, the last topic, counting electrons. Electrical current can be defined as charge per second, equation 20.8. This is actually more of a definition. Just like the current of the Mississippi River down in front of the arch would be the quantity of water per period of time, electrical current is the quantity of charge per period of time going through a wire. We measure it in amps after the French physicist André Ampère. 1 amp equals 1 coulomb per 1 second. And typically, the electrical outlets can deliver a maximum of 15 amps and are on a 15 amp fuse in order to keep the current from being anything more than 15 amps in one of the circuits in your house. Now, what are we going to do with this idea? Look at this example. A current of 2.4 amps is passed through a solution containing copper ions. Could be copper sulfate, copper nitrate, copper chloride. And we do so for 30 minutes, half an hour. And as a result, copper is going to begin to accumulate on whatever the electrode is. It might be a key, it might be a piece of jewelry, it could be a knife or a fork or a spoon, or it could just be another copper electrode that we wanted to make bigger. And we can measure the mass of copper that will cover or be added to the electrode. And here's how. Step 1 in the solution. Since current is defined as charge divided by time, that means that charge is current times time. So we can find our total number of coulombs, 4,320 coulombs in this problem. Part 2. Now we can calculate the number of moles of electrons. In other words, the number of Faradays of electricity. And so we have to convert our coulombs into electrons using the conversion factor that 1 mole is 96,485 coulombs. That conversion factor would be given to you on a test. Now we have our moles of electrons. 4.48 times 10 to minus 2 moles of electrons. Now finally, step 3, we can calculate the mass of copper. We take our moles of electrons and divide by 2 because there's 2 electrons for every copper atom. Remember, it was a plus 2. So we divide by 2. And then we multiply by the molar mass of copper from the periodic table. As a result, moles cancels of electrons, moles of copper cancels, and all that's left is grams. 1.42 grams of copper would theoretically cover this electrode in 30 minutes if the current was 2.40 amps. Now there can be a lot of variations on this problem, and you'll get some on your test. For example, you might be given the mass and asked, how long would it take to electroplate an electrode with 1.42 grams? Or you could be asked, what current is needed for 30 minutes to put 1.42 grams of copper on an electrode? Those are all variations of this kind of problem.